Last time I introduced the task of relation extraction, I described the corpus and the KB that we're going to use, and I proposed a precise formulation of our prediction problem. So now let's talk about how we're going to measure success on this problem. We need to define a quantitative evaluation that can drive a process of iterative development. In this section, I'm going to first make a connection to the software engineering principle of test-driven development. Then I'm going to explain how we'll split our data into training and evaluation data. I'll do a brief refresher on precision, recall, and F-measure. And I'll review the distinction between microaveraging and macroaveraging. And by the end, we'll know exactly how we're going to measure success. When you start working on a new machine learning problem, it's very tempting to jump in and start building models right away because you're bursting with ideas and you can't wait to get started. But whoa, Nelly, that's like driving cross country without a map. There's going to be lots of forks in the road and you won't know which way to go. There's a better way. In software engineering, we use test-driven development. First, write the tests, and then write code and iterate until it passes the tests. In model engineering, we can use a similar paradigm. First, implement a quantitative evaluation. Specify your evaluation data set, choose your evaluation metric, build a test harness that takes a model and generates a score. Then, when you start building models, you can hill climb on this score. And at those forks in the road where you could do it this way or that way, your quantitative evaluation will tell you which way to go. Now, whenever we build a model from data, it's good practice to partition the data into multiple splits. Minimally, a training split and a test split. Actually, here we'll go a bit further and we'll define multiple splits. First, we'll have a tiny split with just 1% of the data. Having a tiny split is super useful, and I encourage you to adopt this practice whenever you take on a new prediction problem. During the early stages of development, you can use the tiny split as training data or test data or both, and your experiments will run super fast. Of course, your quantitative evaluations will be pretty much meaningless, but it's a great way to quickly flush out any bugs in your setup. Then we'll have the train split with 74% of the data. This is the data that we'll usually use for model training. Then the dev split with 25% of the data. We'll use this as test data for intermediate evaluations during development. And for the bake-off, we're also going to have a separate test split, but you won't have access to it, so we won't talk about it here. There's one complication. We need to split both the corpus and the KB. We want each relation to appear in both the training data and the test data so that we can assess how well we've learned how each relation is expressed in natural language. But ideally, we'd like to have any given entity appear in only one split. Otherwise, we might be leaking information from the training data into the test data. In an ideal world, each split would have its own hermetically sealed universe of entities, and both the corpus and the KB for that split would refer only to those entities. So for example, you might have a New World corpus whose examples mention only New World entities like Elon Musk and Bill Gates and Steve Jobs, and a New World KB, which contains only triples about the same New World entities. And then an old world corpus that talks about Daniel Ek and Jack Ma and Pony Ma, and a corresponding old world KB. If we had this, then we could achieve a really clean separation between train and test data with no overlap in entities. But in practice, the world is strongly entangled, and this ideal is hard to achieve. So instead, we're going to approximate the ideal. I think I won't dwell on the details, but we've written the code for you to achieve a good enough split. In particular, the dataset class provides a method called build splits, which lets you specify split names and proportions and a random seed. and it just returns a map from split names to data sets, each containing a corpus and a KB. So now that we have our splits, we need to choose an evaluation metric. We've formulated our problem as binary classification, and the standard metrics for binary classification are precision and recall. So here's an example where we have 100 problem instances. The rows of this table represent the actual labels. 88 are labeled false, and only 12 are labeled true. So this is a skewed distribution. The columns of this table represent the labels predicted by our model. So 95 are predicted to be false and 5 true. Now, there are 89 instances where the predicted label agrees with the actual label. So the accuracy of this model is 89%. But accuracy is not a great evaluation metric, especially when you have a skewed distribution like this. Because even a model that ignores the data and always guesses false can get 88% accuracy just by always guessing false. So instead of accuracy, we look at precision, which says of the instances that are predicted to be true, what proportion are actually true? And recall, which says of the instances which are actually true, what proportion are predicted to be true? So that's great. Precision and recall are really useful, but having two evaluation metrics is often inconvenient. If we're considering a change to our model which improves precision but degrades recall, should we take it? In order to drive an iterative development process, it's useful to have a single metric on which to hill climb. So for binary classification, the standard answer is the F1 score, which is the harmonic mean of precision and recall. The harmonic mean is the reciprocal of the arithmetic mean, the average of the reciprocals. And it's always less than the arithmetic mean. It's pessimistic in the sense that it's always closer to the lower number. So the arithmetic mean of 60% and 25% is, sorry, the harmonic mean of 60% and 25% is 35.3%. Now, the F1 score gives equal weight to precision and recall, but depending on the application, they might not be of equal importance. In relation extraction, we probably care more about precision than recall. And that's because adding an invalid triple to the KB is more harmful than failing to add a valid one. So instead, we could use the F measure, which is a generalization of F1. It's a weighted harmonic mean of precision and recall. And this parameter beta controls how much more importance you place on recall than on precision. So let's say that in a particular evaluation, you have high precision, 80%, and low recall, 20%. The F1 score gives equal weight to precision and recall. So its value is 32%. If we set beta equal to 0.5, we're giving more weight to precision, so the value is 50%. If we set beta equal to 2, we're giving more weight to recall, so the value is 23.5%. In relation extraction, precision is more important than recall. So let's go with F0.5 as our evaluation metric. Okay, another issue that comes up in evaluation scenarios like this is whether to use microaveraging or macroaveraging. We're going to compute precision, recall, and F-score separately for each relation. But in order to drive iterative development, we'd like to have summary metrics which aggregate across all of the relations. And there are two possible ways to do this. Microaveraging gives equal weight to each problem instance, which means that it gives more weight to relations with more instances. Macroaveraging just gives equal weight to each relation. So let me show you an illustration of this. This is an artificial example where I have just 3 relations, and the contains relation has 10 times as many instances as the other 2 relations. It also has the highest F-score. When I compute the micro average and the macro average, well, the micro average gives equal weight to each problem instance. So it gives a lot more weight to the contains relation. And the result is that the micro averaged F-score is very close to the F-score for contains. Whereas the macro average gives equal weight to each relation. And so it's just right in the middle of this range. The micro-averaged F-score is probably not what we want, because the number of instances per relation is kind of an accident of our data collection methodology. And it's not like we believe that the contains relation is more important than the other relations. It just happens to be more numerous in the data that we collected. So we're going to use macro averaging so that we don't overweight large relations. So if you put it all together, the bottom line is that with every evaluation, we're going to report lots of metrics, but there's one metric that we're going to focus on. And this will be our figure of merit. It's the one number that we're going to be hill climbing on. And we're choosing as our figure of merit the macro averaged F0.5 score.